Hello students, we are continuing geometrical isomerism. Now this is your part 3, geometrical isomerism in cycloalkenes. In the previous lesson we have learned geometrical isomerism in cycloalkenes. Now it is cycloalkene. Okay. It has different conditions. Cycloalkenes can show geometrical isomerism about two systems. Number one, about double bond in the ring. It has two conditions also. 3 to 7 membered cycloalkenes do not show geometrical isomerism about the double bond. And condition number 2, cycloalkenes containing greater than equal to 8 members show geometrical isomerism about the double bond. Okay, look at here. This is your cyclohexane ring. This is your cyclohexene molecule. It is a double bond here. So this is the molecule. If the cycloalkene containing 3-membered, 4-membered, 5-membered, or 6-membered rings, these two hydrogen always exist in the cis position. Look at here. These two hydrogen, due to the size of the ring, due to the fixed configuration of the ring, these two hydrogen always exist in the cis form. This is the molecule. This is your molecule. Sometimes this molecule also can be written in this fashion. Look at here. These two molecules are actually identical. Two hydrogens are here and here. Look at here. This is from this view. This molecule is represented like this, and this is from this view. Look at here. If you look at this molecule from this angle, you will find this one. So this molecule can be represented in this way also. So these two hydrogen always exist in the same side, always in the cis conformation. So the two hydrogens present in the 3-membered ring attached to the double bond holding carbon always exist in cis configuration. These two hydrogen always cis. These two hydrogen always cis. These two always cis. Here also. These two are actually same. And these two hydrogen 1, 2, 3, 4, 5, 6, 7. This is a 7-membered ring. These two hydrogen always exist in the cis configuration. Look at here. This is your 8-membered ring. Here it is. Here, this is your 8-membered ring. This one. These two hydrogen exist in the cis configuration. These two hydrogen exist in the cis configuration. This two is cis. This is an 8-membered ring. This one is 8-membered ring. Thus two hydrogens exist in the cis conformation. Okay. Look at here. This is from this view. These two hydrogen are actually cis. These two hydrogen. These two. Now, if we change the configuration, it can have trans also. Trans configuration also. The hydrogen has trans, and this group exists like here. Okay. Now look at here. This view. Look at here. These two hydrogen exist in the trans configuration. Look at here, the hydrogen exists here and the hydrogen exists here. The hydrogen exists here and the hydrogen exists here are in trans configuration. So this is trans. This is trans. Look at here very carefully. This is the observation. This is the view what you are finding in this structure. Look at here. This one is this one. In many books it is written in this fashion. That is, the carbon-carbon bond exists behind the carbon double bond carbon. So it is written in this fashion, in this way. Okay. It can be written in this way also. It can be written in this way also. But these two hydrogen are actually trans. This is possible only when the cycloalkene ring contains more than 8 or more than 8 number of 8 carbons or 8 member rings. Okay, this is possible only when it contains more than 8 carbons, 8 or more than 8 carbons. This is trans. What happens actually? अगर रिंग का आकार बढ़ जाता है तो इसका फ्लेक्सिबिलिटी बढ़ जाता है. When it was 6-membered ring, these two hydrogen can't exist in trans configuration because this ring is very fixed. This is not flexible. But when the number of carbon in the ring increases, its flexibility increases. As a result of that, these two hydrogen can't exist in trans configuration also. So compounds containing 8-membered ring can have cis and trans configuration. Therefore, compounds containing 8 or more than 8 number of carbon show geometrical isomerism. So geometrical isomerism possible only when it is 8 or more than 8-membered ring. But this is not possible for this one, not possible for this one, this one, this one and this one. These are always cis. But it is possible for 8 or greater than 8-membered carbons. Okay. Case number 2, second case, about the ring like cycloalkene. Look at here carefully. Case number 2, about the ring like cycloalkene. Look at here. If you have a compound like this, like this one is CH3 and this one is CH3. Look at here, these two hydrogens are always cis. So geometrical isomerism is not possible here around this carbon-carbon double bond. No GI is possible. No geometrical isomerism is possible. But look at here. Geometrical isomerism is possible around this cycloalkene ring. About the ring, look at here, this 2-methyl. The condition of cycloalkene ring is the ring must contain minimum 2 saturated sp3 hybridized atoms with individually different units. These two are saturated sp3 hybridized carbon containing 2 different units because one is CH3 here, one is hydrogen here, one CH3 here, other is hydrogen here. So the geometrical isomerism can possible around this ring also. Look at here. This is your 6-membered ring. This is your compound. If we substitute this hydrogen by another methyl group or another chlorine like this, or if you substitute this hydrogen by another chlorine groups, what we have in the structure, the compound, this one, here is your chlorine, here is your chlorine. The same thing. So geometrical isomerism is possible, not possible here, but this is possible in case of around this cyclohexane ring also. Look at here, two Cl atoms are in opposite direction, so it is actually trans, and when the Cl atoms are in the same direction, the same side, this is cis. This one is cis. Look at here. These two Cl atoms are actually the same side. So this is cis, and when if you exchange any of hydrogen and chlorine, it will have the trans isomer. These two chlorine are in opposite directions, so it is trans isomer. So cis trans isomerism is possible. Cis trans isomerism is possible around this ring. Here geometrical isomerism is possible. Okay, let us take other examples. Let us take some examples. Number one, this compound, around this carbon-carbon double bond, geometrical isomerism is not possible because this is a 6-membered ring, so it has no flexibility. Now this carbon is sp3 hybridized, but it must contain, to show geometrical isomerism, the compound must contain at least two saturated sp3 hybridized atoms. It contains one, so geometrical isomerism is not possible here. In compound 2, look at here, around the 6-membered ring, around the double bond, geometrical isomerism is not possible. Okay, and it doesn't contain any sp3 hybridized carbon with different groups. In compound 3, around this double bond, geometrical isomerism is not possible, but around this ring it is possible because it contains two sp3 hybridized carbon with two different groups, methyl and hydrogen here, methyl and hydrogen here. So in compound 4, around this double bond, geometrical isomerism is not possible, but it is possible around this sulfur and this carbon because these two are sp3 hybridized atoms with individually different groups. This carbon contains methyl and hydrogen, this sulfur contains lone pair and double bonded oxygen. So around this zone, around this system, geometrical isomerism is possible. Again, in case of compound 5, these two nitrogen atoms are sp3 hybridized. This one is sp3, of course this one is also sp3. So around this system, around this portion of the molecule, geometrical isomerism is possible. This compound contains two double bond, 6-membered ring, so geometrical isomerism is not possible around the double bond, but it is possible around this portion of the molecule. So geometrical isomerism is possible, one cis and one trans form, around these two saturated sp3 hybridized atoms. Now in this molecule parabenzoquinone, the carbon is sp2 hybridized. Again this carbon is sp2 hybridized, so geometrical isomerism is not possible here. In compound 8, these two carbons are sp3 hybridized with individually different units. This one is sp3 hybridized, this one is hybridized. Of course there is a hydrogen, of course there is a hydrogen. So this carbon, these two carbon contains two individually different units, so geometrical isomerism is possible here. In compound 9, around this cyclohexane ring, the geometrical isomerism is possible because here is one phenyl group, other is hydrogen, here is one phenyl group, the other is hydrogen. So geometrical isomerism is possible here. In compound 10, this sp3 hybridized carbon contains two different groups. One is the biphenyl substituent and the other is definitely hydrogen. But there is no other sp3 hybridized carbon with different units. So geometrical isomerism is not possible here. In compound 11, look at here, in this compound, the 2 hydrogen atoms are present in the cis conformations, cis configurations. So this is the cis form, but in compound 12, these 2 hydrogen are in trans configuration. So this is trans. So geometrical isomerism, these 2 are actually 2 geometric forms. These 2 are 2 geometrical isomers, this one and this one. Okay, this is all about geometrical isomerism in cycloalkenes. Thanks a lot.